Alrighty, this is Tracy and welcome to Math 135. We are going to talk about finding an interval estimation of the population mean. Another name for this is finding a confidence interval for the population mean. So we have some online homework in this section, homework 10.2, and some practice problems out of the textbook. Make sure you do those. We do not have online homework like these problems, but they are going to be on your exams. One of the things you're going to need to do is interpret a confidence interval. You'll have to say in words what it means and also find your confidence interval using a t-distribution. I did not go with the online homework because the online homework has us do steps that are unnecessary if we are using technology, and we are using technology. So I didn't want you to be graded on steps that I don't need you to use. All right, let's get our objectives. We are going to interpret a confidence interval for a population mean and find a margin of error from the confidence interval. Our calculators give us the confidence interval. We do not need to do the steps in our textbook to first do all this stuff to find a margin of error and use that to create a confidence interval. Instead, we use our calculators to find us a confidence interval, and from that work backwards to find the margin of error. We're going to talk about the requirements to find a confidence interval for a population mean. We are going to decide whether we are doing a normal Z distribution, a student T distribution, or whether we need more advanced techniques that we aren't learning in this class. We are going to construct, using technology, a confidence interval for a population mean and interpret it. Here, this last step, we're going to need to do a little bit more mathy type stuff to calculate the required sample size to estimate a population mean with a desired level of confidence. So some basic vocabulary. A point estimator is a rule or a process for finding a single value to estimate a population parameter. We typically use a statistic from the sample data. So X bar, the sample mean, is the best point estimator of mu, the population mean. Finding the sample mean is our point estimator. If we have a specific value, that is the point estimate for whatever it is we're studying. So X bar is unbiased and has the smallest mean squared error. Those two things together just mean X bar is the best. So we will be finding the sample mean to estimate the population mean. An interval estimator is a better way of estimating a population mean. Instead of saying, we think it's this value, which is crazy. No sample is ever going to have exactly the right value. What we do is we find a lower and an upper bound, and we say that we have a certain level of confidence. We are 90% confident, 95% confident, whatever, that our true population mean falls between these two values. That's an interval estimator, an interval of values that we believe contains the true population parameter. Using our sample statistics to make predictions about population parameters, like this, is called inferential statistics. And if we want to find a point estimate for the population mean, as we just said, to find a point estimate for the population mean, we just find the sample mean. All right, here we have an example that gives us a confidence interval in some crazy notation, which looks exactly like we're going to get out of our calculators. And we want to interpret this. A study of the ages of motorcyclists killed in motorcycle accidents based on data from the Insurance Institute for Highway Safety found that the mean age of drivers killed was 37.1 years. A 95% confidence interval is, and we get this thing in parentheses, with a low number, 35.18, comma, and then a higher number, 39.02. We want to interpret this and find the margin of error. So our interpretation is that we are 95% confident that the true mean age of motorcyclists killed in motorcycle accidents lies between these two values. If we have a list of data, then the rounding they did to one place past the mean is appropriate. If we are just given, here's your mean, here's your standard deviation, we typically don't go any farther than the mean. We might if it gets to some funky results, but for now, we would round this to 35.2 and 39.0. And then the margin of error we would get by subtracting the mean from the upper value or subtracting the lower value from the mean. So let's go ahead and see what this all looks like. So again, here's our problem and here's our interpretation. We are 95% confident the true mean age of motorcyclists killed in motorcycle accidents is between 35.2 years and 39.0 years old. This is 95% confident because we have a 95% confidence interval. We've got those two boundary values from the set of parentheses. 35.18 rounds to 35.2. 39.02 rounds to 39.0. Another way we could say the same thing, which is also pretty common, the mean age of motorcyclists killed in motorcycle accidents is 37.1 plus or minus 1.9 years. That 1.9 years is our margin of error, and there are several other names for that. The error bound to the mean, the sampling error, all kinds of stuff like that. Okay, so we get that 1.9 by going 39.0, our upper bound, minus 37.1, and that gives us our margin of error. We get the same answer when we go 37.1, our sample mean, minus the lower bound, 35.2. Another way we could get it is by, never mind, that's the easiest way. We'll just stick with that. All right, so what does this 95% confident mean? And here is a link to another instructor who does a video that does a lot of here's what it means. He does a really great job of that. He also does a few more calculations than I want you guys to do. I want you to use your calculators. I think that if we keep it simple, then you can focus on what it means, not on the nitty-gritty details of multiply this, divide this, blah, blah, blah. Okay. So here's a nice picture from this video that kind of talks about what does this 95% confident mean. So if we think back to the central limit theorem, if we have some population and a set sample size, and we go into that population and we get a sample of whatever size and we find the mean and we throw it on a histogram. And then we do that again and again and again for every possible sample with that sample size. We find that we get a normal distribution for our sample means. Most of the sample means cluster tightly around the true population mean, and the further away we get from the true population mean, the fewer samples we get that have that mean, and it follows a normal distribution. So here what we have is we have a normal distribution for the sampling distribution of the sample means. And that shaded area in the middle is where 95% of the sample means fall. So when we find a 95% confidence interval, what we're saying is that the length of that blue area along the horizontal axis, that's the length of a confidence interval. So if we slide that length around, 95% of the sample means we get will have a confidence interval that contains the true population mean. So 95% of the sample means fall into that blue area. 5% fall outside. Alpha is that stuff outside the 95% confidence interval. Those tails contain area where sample means fall that do not have a confidence interval containing the true population mean. Okay, so alpha is 0.05, and each one of those tails contains 2.5% of the area, or 2.5% of the sample means, and that's where we get this alpha over 2 from. We'll talk a little bit about that in some of the next slides. All right, so again, here's another instructor, another textbook, another artist's rendition of a 95% confidence interval. So again, 95% of the 95% of the sample means will fall within a confidence interval that contains the true population mean. So again, if we have the sampling distribution and the means, we have a normal distribution, 95% of the samples fall in the middle, 5% of the samples fall in the tails. Each tail is half of that 5% area, or 2.5% or 0.25. So we have that 95% of the confidence intervals we create from our sample data will contain the true population mean. 5% of these samples that we get will give us a sample mean. We create a confidence interval. 5% of the confidence intervals we get will not contain the true population mean. So again, here's that first instructor's video, another graphic that I really like. So again, here's our normal distribution. And here you can clearly see that that 95% shaded area gives us a size for a confidence interval. Now each one of those bars with the arrows on it represents a confidence interval. As you can see, you get a mean that's right in the middle of that confidence interval. Most of the means have a confidence interval that catches mu in it. For a 95% confidence interval, only 1 out of 20 samples will have a mean that creates a confidence interval, that crazy green one that we see, that falls outside of catching the true population mean. So that's what we mean by 95% confident. Using the techniques that we use, which is our calculator, to calculate a 95% confidence interval means that 95% of the time that we go out, we get a sample, we find a sample mean, we create a confidence interval, we will catch the true population mean in that interval 95% of the time. All right. So, if we want to describe the requirements for finding a confidence interval, when are we allowed to do this? We must have a random sample or a randomized experiment. And we need to have a good study to begin with. For observational studies, we need to make sure we get rid of all these crazy sources of bias. Experiments should be double-blind with a control group and a placebo. If we don't have these things to begin with, none of the calculations we do are likely to have much meaning. We need a good study to begin with. And we a lot of times in our homework, in our textbook, in our exams, will not be told all the details of the experiment. We have to assume that what we're given is good data to begin with coming from a decent study. If not, garbage in, garbage out, our results are meaningless. So if we're going to create our own experimental design, we need to make sure we make a good study to gather data. Otherwise, what we get is garbage. Now, once we've decided that we have a good study and we are allowed to do calculations at all, we need to figure out what kind of calculation we're going to do. We are going to use our calculator to find a confidence interval using either a normal or a Z distribution or a student T distribution. Or we're going to decide we can't do anything because this study is we can't do anything. We need more advanced techniques and we aren't learning those. So, in order to use our techniques, once we've decided it's a good study, we need to know or to have a strong belief that the underlying population is normally distributed or our sample size is bigger than 30. If our underlying population is not normally distributed, and if we have a tiny sample, 30 or below, our methods don't work. We need more advanced techniques that we will not learn in our class. If either our sample size is big enough or the underlying population is normally distributed, then do we know our population standard deviation? If we do, then we can use a Z distribution, a normal Z distribution, because hey, we know our standard deviation. If we do not know the population standard deviation, if all we have is data from a sample, then the normal distribution doesn't work. We need to use what we call a T distribution. Interesting fact, this distribution was first discovered by a fellow who was working for, I think it was Guinness, to create better beer. So stats has really awesome applications out there in the real world. So here in Word says pretty much what we just said. In order to use the techniques that we are learning, you need a population that's normally distributed or a sample size of at least 30. Once we know we can use our stuff, we need to decide whether to use a normal or Z distribution, and we do that if we know our population standard deviation. Or do we use a T or a student T distribution, and we do that if we do not have a population standard deviation, just the sample. And what's the difference? Well, here's a graphic of what those distributions look like. You can see that the normal distribution tends to be more clustered towards the mean. It has little skinny tails. A T distribution has fatter tails. And the smaller our n is, the crazier our T distribution gets. If we have a really big sample size, you sometimes won't see any difference between your confidence intervals using a Z or a T, which is kind of nice. It means you might be able to screw up and nobody will notice. All right, so what are we going to use? Normal Z distribution, student T distribution, or we can't do this problem because it's weird. So here we have that our sigma, our population standard deviation, is known. Our sample size is 24, and the population follows a normal distribution. We have to assume it's a good study, otherwise we're dead in the water. If you're doing this for real, you would make sure you have a good study. So then the next question. Does either our population follow a normal distribution, or do we have a big enough sample? Our population follows a normal distribution, we don't care what n is. Our population follows a normal distribution, we can do something. Now we need to figure out what to do to find our confidence interval. Because we know our population standard deviation, sigma is known, we will be using what we call a Z or a normal distribution on our calculator. Bam, here it is. Assume we have a good study. We have a normal distribution for the population, so yes, we can do something. We know the population standard deviation, so we use a normal or a Z distribution. All right, and here's our next problem. Normal distribution, T distribution, dead in the water because we don't know what to do. We're not that smart yet. So here, sigma, our population standard deviation, is known. N, our sample size is 22, and the population follows a distribution that is skewed right. So we have to assume it's a good study. Is our sample size big enough, or does our population follow a normal distribution? No, neither of these is true. Our sample, our N, is less than 30. We don't have a big enough sample to account for the fact that the population is not normally distributed. Because the population's not normally distributed, we need a big N. We don't have that. We can't do anything with what we learned from our class. Need more advanced techniques. Somebody else takes care of this problem. All right. Again, a normal Z distribution, a student T distribution, or do we need more advanced stuff? A market surveyor wants to estimate the mean number of school children in thousands who read above their grade level in a major city in Florida. She obtains information from 20 school children, so our N is 20, in the city and finds the mean to be 10.3. The population is assumed to follow a normal distribution. So again, we have to assume we have a good study, that the random selection of students was done well and all that good stuff, eliminated sources of bias, yada, yada, blah, blah, blah. So now we ask, is either n big enough? Ooh, n is only 20. If we have a small sample size, we need our population to follow a normal distribution. And it does. Yes, we can do something. To decide what to do, are we going to find our confidence interval using a normal z distribution or a student t distribution? We look and see, do we have a population standard deviation? And the answer is no. We do not know that. If we did, it would have been given. So we are going to have to use the data to find a sample standard deviation, and because of that, we will be using a student t distribution. All right, that's what we say here. Have to assume it's a good study or none of it matters. Our population is normally distributed, so our sample size doesn't matter. We can do something. Is our population standard deviation known? No, if it were, it would have been given. Because it's not, we only have a sample standard deviation. We use a student t distribution. So now we are actually going to use technology. We're going to do it. Look at that, 21 minutes in, and we're going to actually find a confidence interval using our calculators. This is exciting. Okay, a study of the ages of motorcyclists killed in motorcycle accidents based on data from the Insurance Institute for Highway Safety found that the mean age of drivers killed was 37.1 years. The study involved the random selection of 150 drivers. Assume we know the standard deviation for the age of motorcyclists killed in crashes is 12.0 years. Find and interpret a 95% confidence interval estimate of the mean age of all motorcyclists killed in crashes. What is the margin of error? So here we are told we have a random selection of drivers, and this was done by the Insurance Institute for Highway Safety. So there's nothing in there that screams bad study, bias, throw it out, throw it out. So we are going to assume that everything else was done well. Now, in order to do this on our calculator, we need a few things to find our confidence interval, CI confidence interval. We need either the population standard deviation, sigma, to use a normal z distribution, or we need the sample standard deviation, S, to use a student t distribution. So in this problem, we know the standard deviation for the age of motorcyclists killed in crashes is 12.0 years. We know a population standard deviation. We're told. That's what it says right there. We know the standard deviation for this blah, blah, blah is 12 years. So we are going to do a z interval. Oh, and we know we can because look at how huge that sample is, 150 drivers, n is big enough. So yes, we can do stuff. We need the sample mean. Sample mean, oh, there it is. The mean age of drivers killed was 37.1 years. X bar is given in the problem. The sample size is how many people are in our study, n is 150, and we need the confidence level, and that is our confidence interval value turned into a decimal. So a 95% confidence interval is a confidence level of 0.95. 95%, 95 divided by 100 is 0.95. So here is what we are going to put into our calculator. Our sigma, our population standard deviation is 12, X bar, our sample mean is 37.1, and our sample size is 150, our C level 0.95. All right, so here, and a couple slides down, there's a video that shows you the calculator emulator, exactly how to do this, but here's just a quick and dirty. Stat button, arrow over to tests. This is a normal distribution. We have the population standard deviation, so go to 7, z interval. We are going to use the stats that are given, so arrow over to stats. Ignore that data thing because we did not put data into lists where our calculator calculates it. So arrow over to stats, hit enter, arrow down, enter what's given, sigma is 12, X bar is 37.1, N is 150, C level is 0.95, enter, arrow down to calculate, enter, and this is what you should get on your calculator. So here is telling you it's a z-interval. You assumed you knew the population standard deviation, and that set of parentheses is our confidence interval. Our confidence interval is 35.18 to 39.02. And what does that mean? We found a 95% confidence interval, so we are 95% confident the true mean age of motorcyclists killed in motorcycle accidents is between 35.2 years and 39.0 years old. We rounded here. It worked out nicely to round because it still puts our mean right smack dab in the middle of our confidence interval. We don't round if it shifts things around too much. Okay. To find the margin of error, we, as we said before, take the upper boundary for our confidence interval, subtract off our mean, and you get the same thing when you take the mean and subtract off the lower boundary, 1.9 years. And again, this is the same exact problem we started with, so you can flip back and interpret it exactly the same way we did before. So here's a video link to do this on
All
the
right,
TI.
let's go ahead and use our TI graphing calculator in order to figure out our confidence interval. And this should be a lot easier than the many steps that are involved in doing this more by hand. So we are back to our favorite button in our stats class, the stat button. So go ahead and hit stat. And now we are going to be doing some tests. Even though confidence intervals aren't technically tests in the sense of hypothesis testing, which we'll be doing later, it's still a sort of a test. So we arrow over to tests, and then we have this big list here. Now, we figured out for this problem that because we have the population standard deviation, we are going to be finding a confidence interval using the z, the normal z distribution. And if you look down your list of options, number 7 is a z interval. That is a confidence interval using a normal distribution, which is what we use when we are finding a confidence interval for a population mean where the population standard deviation is known. So go ahead down to that. Now, if we had entered data into our lists, then we would use the data that is flashing here for you. That's not what we're doing. For this problem, we were given our summary statistics. We were given mean, standard deviation, all that good stuff. So we are going to go ahead and arrow over to stats and hit enter to say we are using the stats given. We are not finding those little pieces from the data. So once you hit enter on stats, you can arrow down. Now we have the population standard deviation given in our problem. And remember, a population standard deviation is that sigma. Kind of looks like an O with a crazy toupee. So we were told that the population standard deviation is 12. So you can enter or arrow down from that. We were told that the sample mean, because that's all we have is the sample mean. We are trying to figure out about what the population mean is. So we use our sample mean, 37.1, and enter or arrow down. Now we go to our sample size, and we are told in the problem that we have 150 subjects in this study. And now we go down to that confidence level, which we are given usually with a percent, so we need to turn that into a decimal. A 95% confidence interval is a 0.95 confidence level. Always double check that. Our calculator either defaults to 0.95 or uses the one from the problem before. I'm not really sure. I know that if you start completely fresh, it defaults to a 0.95. All right, so enter, enter, and bam, that quickly, there is our confidence interval. As always, if you have any questions about how to do this stuff, let me know.
Here we have a new problem. It's going to look a lot like the last problem, but there are a couple of differences, so make sure you're paying attention so that you don't get caught up on these differences. A study of the ages of motorcyclists killed in motorcycle accidents based on data from the Insurance Institute for Highway Safety found that the mean age of drivers killed was 37.1 years. The study involved the random selection of 150 drivers. Assume the sample standard deviation for the age of motorcyclists killed in crashes is 12.0 years. Find and interpret a 90% confidence interval estimate of the mean age of all motorcyclists killed in crashes. What is our margin of error? So here, we still have a problem where we assume we have a good study. We don't have anything in there screaming, this is terrible, it's biased, it's, throw it out. So we assume we have a good study. Our N of 150 subjects in the study is big enough that we don't care what the underlying population distribution is. We have a sample mean, and here we have a sample standard deviation, not a population standard deviation. We will be using a T distribution, a student T distribution, not a normal Z distribution. And in this case, we are going to find a 90% confidence interval. We are less confident in this problem that our true population mean will fall within the confidence interval that we give. So here is what we are going to need for our calculator. We need our sample mean. We need the sample standard deviation, and we use S for sample standard deviation. S, that is what's going to go in our calculator now, not sigma. So our sample standard deviation is 12, our sample size is 150. Our confidence level is that 90% confidence interval we want to find divided by 100, so 0.9. And again, a couple slides down, you'll have a full video length showing you hitting all the buttons on the calculator, but quick and dirty, stat button, arrow over to tests. We want a T interval. We are finding a confidence interval for a population mean with a T distribution because we only have a sample standard deviation, not a population standard deviation. We're going to use the stats given, not data, so arrow over to stats and hit enter, and then arrow down to do the rest. Enter your mean, 37.1, our X bar, our SX, sample standard deviation of 12, and sample size of 150. C level, confidence interval, 90% divided by 90 divided by 100 is 0.9. Enter on calculate. And this is what you should see on your screen. And you'll see we have a different confidence interval, but it's the same format, parentheses with a lower bound and an upper bound. We are 90% confident the true mean age of motorcyclists killed in motorcycle accidents is between 35.5 years and 38.7 years old. So we again round to the same value or the same number of decimal points as the sample, mean, and standard deviation that are given. It works out nicely. We take that 38.7, subtract 37.1, we get 1.6. We take 37.1, subtract 35.5, we get 1.6. So our margin of error works out nicely. The mean age of motorcyclists killed in motorcycle accidents is 37.1 plus or minus 1.6 years. Remember, again, this is a 90% confidence level. Our margin of error is 1.6 years. And again, here's a video
Alrighty,
link
let's go
to
ahead and
find
use
our
our TI graphing
interval.
calculator in order to find a confidence interval where we do not know the population standard deviation. So now we are going to do the same thing we just did, but for a T test, or I'm sorry, a T distribution instead of a Z distribution. So again, we are back to our favorite button in stats class, the stat button. A confidence interval is still a sort of a kind of test, so arrow over into tests, except now we do not know the population standard deviation. We have a sample, and from that we calculated a sample standard deviation. When all we have is the sample standard deviation, we are now going to find a confidence interval using a T distribution. So T interval. And if we look down here, all this list of things, we find that number 8 is our t-interval. So we can either type in number 8 or arrow down and enter. And again, we do not have our data in lists. We were given a problem in which we were told a sample mean, a sample standard deviation. We're not calculating it. This data button, this here is if we have all of the individual sample readings in our lists and we have the calculator calculate the sample mean and standard deviation and the sample size. We're not doing that, so we arrow over, we hit enter on stats to say switch to stats, and now we arrow down. For our problem, we are given a sample mean x bar of 37.1, either enter or arrow down to our sample standard deviation. Remember, we use the letter S for a sample standard deviation. For the population, it was that sigma, which looked like the little O with the toupee. We just used the letter S for a sample standard deviation of 12. And we go down to our sample size. We are told in the problem 150 subjects in the study. Our confidence level for this problem is a 90% confidence interval. So for a 90% confidence interval, our confidence level is 90 divided by 100, or 0.9. Make sure you check that. And enter to calculate, and there it is. Here is our confidence interval for a population mean when we only have a sample standard deviation, not a population standard deviation.
And here's another problem. The Water Works Commission needs to know the mean household usage of water by the residents of a small town in gallons per day. Assume that the population standard deviation is 1.5 gallons. The mean water usage per family was found to be 17.5 gallons per day for a sample of 543 families. Construct and interpret the 98% confidence interval for the mean usage of water, and what is the margin of error? So this problem is just like what we did. We need to decide, well, we're going to assume it's a good study. We're not given any red flags saying this is a terrible study, don't bother. We assume we have a good study. We don't have anything telling us about the shape of the underlying population distribution, but we are taking a sample of 543 families. Our sample size, N, is bigger than 30, so we don't care what the underlying distribution for the population is. N is 543. We are trying to find a confidence interval, a 98% confidence interval, so our confidence level is 0.98. We need to decide if we are using a normal Z distribution or a student T distribution. In this problem, we are told the population standard deviation is 1.5 gallons. That means we are going to use a normal Z distribution. A normal Z distribution because we know the population standard deviation. And then we have the sample mean. The mean water usage per family was found in this study for our sample to be 17.5 gallons per day. So we are going to go ahead and take all this stuff and put it in the calculator. So this is what goes into the calculator. We are going to go to the stat button, arrow over to tests, because we know the population standard deviation. This is a Z interval. Because we are using stats that are given to us, we did not put our data into lists, and we're not asking our calculator to find the sample mean or sample standard deviation. We arrow over to stats and hit enter, then arrow down to enter in sigma, population standard deviation of 1.5, x bar, sample mean of 17.5, N, sample size of 543, confidence level, C level, our confidence interval as a decimal, 98% confidence interval, 98 divided by 100 is 0.98. Arrow down to calculate, hit enter, and bam, this is what we get. Now, This time we are going to stick with the confidence interval as it's given, because if we round, we would round the 17.35 up to 17.4 and the 17.65 up to 17.7, and our mean's not really in the middle anymore, so that just isn't as pretty. So we are 98% confident the true mean household water usage by the residents of this small town is between 17.35 and 17.65 gallons per family per day. The mean household water usage is 17.5 plus or minus 0.15 gallons per family per day at a 98% confidence level. And again, we got that margin of error of 0.15 by taking upper bound 17.65 minus the mean to get 0.15, and take the mean minus the lower bound, get the same value for your margin of error. For that problem above, do we expect a 90% confidence interval to be bigger or smaller than the 98% confidence interval? And then repeat the same problem above for a 90% confidence interval. So here, again, I pilfered another instructor's graphic to illustrate confidence intervals, because our books, it's not that great as far as the little pictures go. So here, we can see the 80% confidence interval in the middle. The size of that is relatively small because we only need to be 80% confident. We only need 80% of the confidence intervals we have to contain the true population mean. So that confidence interval is not going to be as big. It doesn't hold as many samples that contain the true population mean. 90% confidence interval is a little bigger than that. 95% confidence interval is bigger than that. The bigger the confidence interval, the higher the confidence level. So a 90% confidence interval has a smaller confidence level than 98%, so it has a smaller area, so it's going to be a smaller interval. And let's calculate it. Again, our population standard deviation given in the problem, 1.5, our sample mean given in the problem, 17.5, our sample size given in the problem, 543, but our confidence level is only 0.9. So we do exactly the same thing. Stat button, arrow over to tests, Z interval because we know a population standard deviation, arrow over to stats and hit enter because we are using summary statistics provided, not data that we entered into a list. Arrow down to enter all of the stuff given, including that confidence level, and bam, there it is. There's our Z interval. Confidence interval for a population mean where we know the population standard deviation, so we use a normal distribution. We are 90% confident the true mean household water usage by the residents of this small town is between 17.39 and 17.61 gallons per family per day. Round the same way we did on the last problem because we're comparing it to the last problem. Our margin of error, take the upper bound minus the mean minus the lower bound, get the same value, it's only 0.11. And again, yes, as we said, this confidence interval is smaller than the last one because 90% is a smaller area than 98%. We are less confident that we are truly containing the population mean. If we want to be more confident, we need to have a bigger interval to catch more stuff. All right, here we're switching gears a little bit. We want to calculate the required sample size to estimate a population mean with a desired level of confidence. This is before the study begins. How big of a sample do we need so that we can say we are 95% confident that our true population mean is whatever sample mean we get plus or minus only 3 inches, 2 IQ points, 0.5 gallons. We want to in advance decide how confident we are and what our margin of error is, and then go out and create a study that's big enough to make it happen. So our calculator does not just bam, 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 here are a few buttons and it pops out for us. We have to do some calculations. Had we been doing all the calculations the long way, you'd be more comfortable with this, but we're not going to have as many of these types of problems on the test, so I didn't want to spend as much time doing the crazy calculations. We have a formula for the margin of error, which is the letter E. It is Z sub alpha over 2. And what that is the Z-score for a normal distribution to get you the area in the tails. That is how many standard deviations our sample mean can be from the true mean to have a confidence interval that contains the true mean. That's a Z-score. So we're going to find that in our calculators, that part. And then we multiply that by the size of the standard deviation for the sampling distribution of the means. Now, if we remember, the standard deviation for the sampling distribution of the means, back in the previous section, is the population standard deviation divided by the square root of the sample size. So here we kind of have a picture of this. Here we have that Z alpha over 2. If we have a 95% confidence interval, we want the area, the stuff in the middle, to be 95% of all of our sample means. That means the area in the tails, the area, the sample means that do not have a confidence interval that contains the true population means, is what's left. 95% of the samples we get have confidence intervals containing the population mean. 5% don't. That means 5% divided by 2, 2.5% of our sample means are too low to contain the true population mean in the confidence interval, and 2.5% of the sample means are too big to have a confidence interval that contains the true population mean. The Z down there is the Z-score. That tells us how many standard deviations away we are from the true mean before our samples are not good anymore. So what we are finding is we are finding a Z-score, but also a percentile. We want to find the standard normal distribution value that cuts off 2.5% of the data values. Okay. Oh, and also again, remember that when we're dealing with the sampling distribution of the means, that our standard deviation is the population standard deviation divided by the square root of the sample size. So here, to find that Z alpha over 2, we would use the inverse normal button. And we were doing that back when we were dealing with normal distributions. So we would go to our distributions. We would go for inverse normal. That's number 3. We would put in whatever our alpha over 2 is, and then 0, because this is a standard normal curve. The mean is assumed to be 0. And 1 for one standard deviation. And then we're going to make the results positive because we don't care above or below. We just care how many standard deviations. Rearrange that formula we just had to solve for n. And this right here, bing, 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 this is what you want in your notes for the exam. To find the sample size, to calculate, to find a confidence interval for a population mean with a certain confidence level and a certain margin of error, this is your formula. Your sample size is that Z-score we found above, the inverse normal, alpha over 2, 0, 1, times the population standard deviation divided by the margin of error squared. Here's an example. Assume we want to estimate the mean IQ for the population of statistics professors. How many statistics professors must we randomly select for IQ tests if we want 95% confidence that the sample mean is within 2 IQ points of the population mean? Suppose that IQ tests are designed so that the mean is 100 points and the standard deviation is 15 points. So we've got that formula. We know that we are trying to find the sample size. we need to calculate our z alpha over 2, and we're going to do that knowing that alpha is 5. Our confidence level is 95%. That means we have 5% off in the tails. That's alpha. That means each tail has 2.5%. 2.5% of sample means that don't fall in a confidence interval. That don't have a confidence interval that contains the true population mean. So alpha over 2 is 2.5%. We're going to use the inverse norm and find that z-score. We know the population standard deviation is 15 points. It's given to us. And we know our margin of error is 2 because we want confidence that the sample mean is within 2 IQ points of the population mean. That's your margin of error. So here's our formula. To find that z alpha over 2, 95% confidence interval, subtract from 100, take 5%, divide by 2, and turn it into a decimal. Alpha over 2 is 0.025. So to find z 0.025, we go inverse norm. We put in 0.025, 0, 1. When we hit enter, we're going to get a negative 1.96, but we don't care. We just want to know how many standard deviations from the true population mean our sample can be to have a confidence interval that catches the true population mean. So that goes into our formula as that z alpha over 2. Multiply it by the population standard deviation, 15, given, divide by the margin of error, 2 IQ points, given. Bam, bam, bam in your calculator, 2.16, and if there's anything after that, we round up. So we need a minimum sample of 217 statistics profs to find a 95% confidence interval for IQ score with a margin of error that is less than 2 IQ points. Another example of doing the same thing, finding a sample size. The electric cooperative needs to know the mean household usage of electricity by its non-commercial customers in, I think that's kilowatt hours per day. I think so. I'll just go kWh just in case that's wrong. They would like to estimate to have a maximum error of 0.1 kWh. A previous study found that for an average family, the standard deviation is 2.3 kWh, and the mean is 15.2. If they are using an 85% level of confidence, how large of a sample is required to estimate the mean usage of electricity? So we have that formula, which again needs to be in your notes. We know we need to find a z alpha over 2. That is going to be a z-score, a percentile, that we're going to calculate using the inverse norm in our TI. We need to have a standard deviation, and even if all we have is a sample standard deviation, actually we're going to go ahead and use that. We're given that standard deviation is 2.3, and we need a margin of error. So the maximum error we want is 0.1. That is our margin of error. So let's go ahead to that formula. To find the z alpha over 2, we have an 85% level of confidence. So alpha is 100% minus 85%. 85% in the areas in the middle leaves 15% left for the tails. Take that 15, divide by 2 to find the area in a given tail. To find the z-score, the number of standard deviations from the true mean that is, to cut off that 7.5% area on the lower tail, we go inverse norm, type in that area, 0.05. Because we are looking for number of standard deviations, we're assuming that we are having a mean of 0 and a standard deviation is 1. So inverse norm, 0.05, comma 0, comma 1. Pop that into your calculator, you get a negative number. We don't care. We don't care that this is below the mean. We just want to know how many standard deviations away. So we take that 1.4 and we pop it in for the first thing in our formula. multiply it by the standard deviation that's given in the problem, 2.3, divide by the margin of error, or the maximum error that's given in the problem, 0.1. Square the result, get 1096, doesn't matter what comes after, we round up. We need to randomly sample at least 1,097 families to estimate the mean household usage of electricity by non-commercial customers to get an 85% confidence interval with a maximum error of 0.1 kWh, kilowatt hours, I think. All right. As always, if you have questions, please, please, please contact me. Oh, and here's what it looks like on your calculator. Sorry. Inverse norm, that was your second VARS. Go to number 3, inverse norm, enter the area, and 0 and 1 are already given, and there you go.